Good afternoon or evening, everybody. My name is Rob Thompson. I am the president of the Canadian Association of Physicists, and it is my privilege to welcome you to the 2021 Herzberg Memorial Public Lecture. It is also my privilege to be speaking to you now from the city of Calgary, and I'd like to take this opportunity to acknowledge the traditional territories of the people of the Treaty 7 region in southern Alberta, where I'm seated, which includes the Blackfoot Confederacy, comprising the Siksika, Piikani, and Kainai First Nations, as well as the Tsuut'ina First Nation and the Stoney Nakoda, including the Chiniki, Bearspaw, and Wesley First Nations. The city of Calgary is also home to Métis Nation Region 3. Many of us, I know, were shocked and saddened by the news from the site of the former Kelowna residential school. And I would now like to ask for everybody to spend a minute of silence and reflection on the impact of the news from Kamloops this week. Thank you. We could get the next slide, please. We're here, as we've done every year, except last year, for the annual Herzberg Lecture of the Canadian Association of Physicists. Dr. Gerhard Herzberg was a renowned physicist, chemist, and astronomer here in Canada, and was the president of the association from 1956 to 57. In 1970, we established the Herzberg Medal as the recognition of top early career researchers in the field. And in 1971, Dr. Herzberg was awarded the Nobel Prize in Chemistry for his work in molecular spectroscopy. Sadly, Professor Herzberg passed away in March of 1999 at the age of 94, and he generously left a bequest to the association, which has allowed us to launch this lecture series. This is one of the highlights of my year as president. It was my good fortune to meet Dr. Herzberg several times. The first occasion was in 1988, when I was a very junior graduate student, and my supervisor, who was Dr. Boris Stoichev, Dr. Herzberg's biographer, brought Dr. Herzberg to the lab as the first person I ever explained my thesis work to. Let's say that Dr. Herzberg proved that his reputation for kindness was well deserved. And with that background, I'd like to invite Richard McKenzie to come to the stage and introduce our 2021 Herzberg lecturer.
Bonsoir et bienvenue à toutes et à tous. Il me fait grand plaisir de vous présenter le conférencier Herzberg de 2021. It's a great pleasure and an unqualified honor to introduce the 2021 Herzberg lecturer, Professor Frank Wilczek of MIT, Shanghai Jiao Tong University, Arizona State University, and Stockholm University. Professor Wilczek, I'll call him Frank from now on, is undoubtedly one of the world's leading theoretical physicists, and he has been a dominant force in his home turf of particle physics and far beyond for almost half a century. Indeed, Frank exploded out of the starting blocks in the early 1970s, laying the foundations for the theory of the strong interaction in the course of his PhD work for which he shared the Nobel Prize in 2004. Since then, over the intervening almost 50 years, Frank has published something in the neighborhood of 500 research papers and at least 5 books that I'm aware of. The most recent book, entitled Fundamentals, 10 Keys to Reality, came out just earlier this year. If Frank's PhD work on the strong interaction established him as one of the leading figures of theoretical physics, he's in the intervening years made many other signature discoveries. I could probably name about 20, but I'll restrict myself to 3 biggies. He proposed a particle which is still very interesting these days, named the axion. More recently, he proposed time crystals, and he is one of the founders of the subject of the lecture this evening. In addition to the Nobel Prize, Frank has won a very long list of awards, honors, distinctions, etc. So in the interest of time, I'll only mention the big one that he has yet to receive. I'm talking, of course, about the Stanley Cup. Keep your skates sharpened, Frank. I'm sure it's coming. Before inviting Frank to the virtual stage, I just have to mention one logistical detail to the audience. The talk, which will be something like 40-something minutes long. After the talk, Frank will be happy to answer questions from the audience. If you're watching on Zoom, you're encouraged to submit questions either during or immediately following the talk via the Q&A button, which should appear at the bottom of your screen. If you're watching the talk on YouTube, questions can be submitted via the Google form pasted in the video description. If you're a bit camera shy, don't worry about it. In fact, if you're not camera shy, worry about it, but you won't be asking the questions. I'll be asking the questions. So don't be shy about asking a question if you were afraid to talk in front of a large audience. Anyways, with that little logistical detail out of the way, please give a warm welcome to Frank Wilczek, who will be giving his talk entitled Quanta of the Third Kind, Anions.
Yeah. Thank you very much, Richard, for that gracious introduction. I think I've got a lot of work to do before I'll be anywhere near the Stanley Cup, but I'll take it as a homework assignment. And without further ado, let me go into share screen and begin my presentation today, which will be as advertised about the subject of anions. So physicists for decades, since the early days of quantum mechanics, really for about a century now, have classified quantum particles into 2 types, 2 kingdoms, the kingdom of bosons and the kingdom of fermions. And it was thought, and you find so-called proofs in quantum mechanics textbooks, that these exhausted the possibilities. Bosons and fermions exhibit very different behavior when you bring several of them together. So whereas in quantum mechanics, we achieve a unified description of all kinds of matter at the single particle level, so that, for instance, electrons, which we usually think of as waves, as particles, can also be described as waves, and photons, which we usually think of as waves, can also be described as particles. Both of them have a common description in terms of wavicles. But when you bring more than one particle together, quantum mechanics gives different possibilities, two big divergent classes of particles. And basically, the behavior of bosons is that they want to do the same thing, while fermions refuse to do the same thing. This is called quantum statistics for rather obscure historical reasons. But it supplies, in effect, a powerful new kind of force that has no classical analog. When we discuss the fundamental forces of nature, we usually talk about there being four of them that we know at present: gravity, electromagnetism, and the strong and weak forces. But the effect of quantum statistics can compete with all those forces and gives a kind of effective force whose roots are in the deep structure of quantum mechanics and has striking physical consequences. Let me show you a few. So electrons, neutrons, and protons are in the fermion kingdom. And it's the fact that electrons are fermions that prevents all the electrons in an atom from occupying the same state of organizing themselves so they can hug up close to the nucleus. Ultimately, it's Fermi statistics that's responsible for the shell structure of atoms, for the different levels that get occupied as you have more and more electrons in an atom. And it's responsible for the periodic table. It's also the fermion statistics of protons and neutrons is responsible for the shell structure of nuclei. I can mention here that when Freeman Dyson proved the stability of matter, it was absolutely necessary to invoke the Fermi statistics of electrons. So Fermi statistics is really what makes matter solid. When stars exhaust their nuclear fuel, so they no longer can support themselves against the pressure of gravity by the thermal agitation of nuclear fuel burning, if they're not too big, they collapse into white dwarfs. And when you have a white dwarf, what you have is a big piece of matter with a mass of roughly the sun, supported by the refusal of electrons to do the same thing, to occupy the same quantum state technically. So here you have a kind of giant atom held together not by electric forces, but by gravitational forces, and held from collapsing by quantum statistics, the quantum statistics of the electrons, which are fermions. Similarly, if the stars are somewhat bigger and collapse, they become what's called a neutron star, which is, as the name suggests, mostly made out of neutrons. Here, the Fermi statistics of neutrons is what supports the star, providing an effective repulsion, which allows the star to maintain itself against the very, very strong gravity of this extremely compressed form of matter. So this can be thought of as a giant nucleus held together not by the strong force, but by the gravitational force, but guaranteed against collapse, as are regular nuclei, by Fermi statistics. So Fermi statistics can be very, very powerful, generate very powerful effective forces. No less remarkable are the qualitative implications of boson statistics. Photons are an outstanding example of bosons. And it's because of the tendency of bosons to do the same thing, that want to do the same thing, that it's possible to induce photons to form lasers. In lasers, you have photons all of the same frequency, moving all in the same direction. So they're very happy, and they're doing the same thing, and it's the quantum statistics, the boson statistics of the photons that makes laser action possible. Here's a slightly more technical version of it, where you see if you have energy levels of cold matter, then bosons want to all go to the lowest energy state, whereas fermions are forbidden to go to the lowest energy state because no two fermions want to be in the same state, so they accumulate into higher and higher energy levels. This is the origin of shell structure of atomic nuclei and atoms, as I mentioned. And on the boson side, this is the origin of laser action. Okay, so that was the situation that physicists thought was universal and exhausted the possibilities until the late 1970s, when some of us realized theoretically that the proofs in textbooks have a loophole. The arguments are completely wrong, but if you, in most of the textbooks from that period, but you can fix up the proof in a world of 3 or more dimensions. You can find a different mode of analysis that gives the same result that the 2 possible behaviors of multi-particle accumulations, assemblies in quantum mechanics are either that they behave like bosons or that they behave like fermions. However, we realized a loophole that if we lived in a space of 2 dimensions, there would be many other possibilities. Here is a situation where less is more. And the deep origin of this, which I won't explain in any detail, is that whereas you can have knots in 3 dimensions, in 3 space dimensions, in 4 dimensions or more, knots can always be untied continuously. All knots in 4 dimensions are trivial. If you like, during the question period, I can elaborate more on why that's the key mathematical fact here. So in 1982, I brought a lot of these ideas together and named the christened the new kind of particles as anions. From the physical point of view, the remarkable thing about anions is that they have a kind of memory. Anions, or more precisely, their wave functions, which are their primary description, keep track of how many times and in what patterns they've wound around one another. So that's what they keep track of. That's what their wave function has imprinted on it, a record of how they've wound around each other. Technically, how these world lines, that is, you take the positions as a function of time, you get lines that describe the motion of the anions, how these world lines get entangled. The topology of this kind of entanglement leaves an imprint on the wave function. And experimentally, then, if you do a complex motion of the anions, it affects what you can read out from the wave function. So you can, as we'll see, you can attempt to use this to do useful computations, because knots can get very complicated and encode a lot of information. So the technical mathematical term for this kind of topology, tangling up of strands in 3 space dimensions or 2 + 1 space plus time dimensions, is called braiding. And you can see from this picture why it's called braiding. It's the key mathematical fact that allows beautiful arrangements of hair that won't unravel if you just tie the end with a rubber band. Now, of course, you might have thought that this was a very academic kind of result because we don't live in a two-dimensional world. But we can create such worlds and study them and use them. And in fact, in a very real sense, nowadays, we do spend a lot of our time interacting with two-dimensional worlds. A modern computer, modern standard computer like this Intel central processor here, is based on essentially two-dimensional arrangements and motions of electrons. So that's when you see these little chips. So, so that was a theoretical possibility. That is, it was consistent with the basic principles of quantum mechanics that there should be new kingdoms of particles, but we didn't have any candidate occupants of this kingdom until 1984, when I showed that stable concentrations of energy, that is what we call particles or quasi-particles within a certain state of matter. The way, if you lived within that material, you would think of them as just particles. They are the stable concentrations of energy within this state of matter. That in this state of matter called the fractional quantum Hall effect, that they would be a kind of fermion. They would be neither bosons nor fermions, but something new and different. Here, I'm very proud of this paper, so please indulge me. This was the paper. And at the time, I thought this prediction would be verified in a matter of months. At that time, I was, I guess, spoiled by what had happened in QCD, but also spoiled by the fact that I knew that where particle physics had the reputation for being slow because you have to build elaborate accelerators and make big collaborations and interpret complex data to get the information out. I thought, oh, this is much, much simpler. This is condensed matter physics. It doesn't take a big, it doesn't take Fermilab or CERN or a big facility and should be a piece of cake to check out this prediction. I thought it would be a matter of months. Instead, it took more than 35 years because although things don't have to be big, it turns out they have to be very pure. They have to be very well insulated from the external world. And you have to make very precise kinds of measurements, very ingenious measurements in order to tease out this behavior. But finally, in April 2020 came good news on the cover of Science, announcing the observation of exotic statistics. What was done here in this experiment was basically people built a tiny accelerator where you could produce the anions in this fractional quantum Hall state and bring them into, produce two streams of them and bring them into collision and study the probability that they come out at different angles as a function of how many there are. So as a function of how the impacts or the collisions affect the transmission of the particles. And what the experimenters found was that they got a result which was in between the behavior predicted for bosons and the behavior predicted for fermions. So roughly speaking, fermions, when they, if they want to cross each other, they're stopped because they can't occupy the same state, so they refuse to cross each other. Whereas bosons love to cross each other, and you get an enhancement when two of the scattering, when two bosons come together. And you can predict quantitatively the size of these effects. And what the experimenters observed was an in-between result, which was completely consistent with our prediction for the quasi-particles in this state of matter. So that was nice, but a little indirect because you weren't really accessing the most basic effect, which is this memory of braiding, a memory of how the particles braid around each other, how they've moved around each other. But it didn't take much longer, and when in 2020, June of 2020, there was even better news. This was a paper that appeared, I believe, also in Nature, but maybe it was Science. Yeah, in Nature, rather than Science. This is the preprint version, where this was an observation not of a kind of statistical blockage, but a statistical effect of how much blockage there was of these beams crossing each other, but really the most basic Anion braiding behavior, this kind of imprinting on the wave function. This is a false color and cleaned up version of the actual apparatus. It's very small, so these kinds of accelerators are really not what you think of when you think of Fermilab or CERN. These are very tiny things. That's good if you want to use them for technology. And what they did was vary the magnetic field that this little two-dimensional layer, and the blue is an ocean of electrons, that this two-dimensional layer is subject to. And when you do that, theoretically, you occasionally pop an Anion into the middle. Now, the other Anions have two ways of going around, this top way or this bottom way. In the fractional quantum Hall effect, I'm sorry, so we want them to get from here to here, from the left-hand top to the left-hand bottom. They can only move unidirectionally, so they, at one point or another, they have to leap across what's called a barrier, a small tunneling barrier, to reach this destination. And they can take two paths. They can take this upper path along the top and make the transit along the right-hand weak link, or they can make the transit along the left-hand weak link and more directly reach the apparatus which measures the total current. So these two paths, if you think about it, are braided around each other. So the relative behavior of Anions which go over the top or the bottom has imprinted on it which way it went around. And that affects the total amount of current you get when the two are added together. The two paths are added together. And there's a drastic change of a predictable magnitude each time an additional Anion is popped into the middle. And here is the stunningly beautiful result of their experiment, which shows the predicted jumps in the current as you pop Anions in and out by adjusting the magnetic field. And here you can see Michael Manfra, who was the senior experimentalist on this project, very pleased. It has it really, I think, broke the log jam. Now they've found a number of tricks that are going to make future progress much easier and rapid. And here you see what the actual apparatus looks like. It does fit within a laboratory, but it requires a lot of cooling, a lot of instrumentation. As you see, it's a sophisticated thing. And maybe in retrospect, it's not surprising that it took 40 years almost to get it all right. For later purposes, but also because it's interesting in its own right, let me mention that there were earlier beautiful experiments in China that had already kind of done engineering versions of anions, specially crafted little units that in effect make little particles within circuits, and you can braid around those. So this is not in a state of matter, but taking that kind of behavior of quasi-particles in matter as an inspiration to make quantum mechanical objects in circuits that have anion behavior. And they had had that emulating anion behavior in those kind of circuits already in 2016, if I remember correctly. So, so anions are real. Now we know for sure. They've been on the theoretical drawing board for, as I mentioned, 40 years or so. And there are thousands of papers on the subject. But the experimental, the positive experimental literature is just beginning. And the prospects, so what are you going to do with it? What are the prospects for using this new kind of phenomenon? Well, besides the fractional quantum Hall effect, many other interesting states of matter and, as I've already alluded to, engineered systems are predicted to contain various kinds of anions. It's become a theoretical cottage industry to examine states of matter in 2 dimensions and that support anion behavior. And it's in 2 dimensions, once it has a chance, it's almost generic behavior. Many, many predicted states of matter in 2-dimensional systems support anions of different kinds. Of different kinds means that the way they imprint the braiding information on their wave function differs in detail. Theory got way ahead of experiment, but now experiment is catching up. And I think physicists will be exploring these anionic worlds for years to come, just because they're interesting, and these new, deeply quantum mechanical states of matter are fascinating to theorists and conceivably will find surprising applications, although it's not clear what they'll be. That's why they could be surprising. However, one application is very real, very promising, very specific and promising. There's a big research effort aimed at using anions to do topological quantum computing. As I already mentioned, the essence of anions is that their wave functions remembers the knots that or braids that their world lines formed as they move, and braids can get very, very complicated. You can store and process information by manipulating braids. So by moving anions in physical space, you can perform computations in their wave functions, or we say in Hilbert space. You can translate motion of anions directly into information processing. The great potential benefit of this approach to quantum computing, as opposed to other approaches, is that it addresses perhaps the most challenging aspect of quantum computing. That is that it's very, very delicate. The quantum wave functions of macroscopic material systems, in other words, quantum computers, can contain a lot of information, but that information is very, very delicate. If you don't shield the system from the external world, so to speak, is constantly interacting with it and making measurements. And when you make measurements of quantum mechanical wave functions, they collapse. Nowadays, there are much more sophisticated behaviors, and many of my colleagues would be furious if I mentioned collapse of the wave function. But the more sophisticated, but the good old collapse conveys the main message, which is that quantum mechanical information is usually very, very delicate. And that's been the big challenge of trying to achieve a decent sized quantum computer that doesn't make mistakes all the time. However, with Anions and topological quantum computing, you have a lot of noise immunity because the result, the way the information is imprinted, as I've mentioned several times, depends on the topology of how these lines get entangled, not on the details of their small scale motion, but only on the global entanglement, the global topology of how the world lines are forming braids. So that if the external world makes, say, this guy jiggle a little, it doesn't matter. That doesn't change the topology. And so you have, with Anions, you have a lot of noise immunity. So although the Anions are difficult to make, now there's been dramatic progress in making them. And once you've made them, they are very, very friendly to the program of manipulating and storing quantum information with much less contamination from noise from the external world. I should mention, by the way, that you really do need to interact with the external world. Otherwise, your quantum computer can be very, very clever, but it's just a black box. If you want to put data into it and get results out of it, you do have to interact with it. And so it does have to be open to the external world. Microsoft has invested a lot of money and manpower into this program of enabling topological quantum computing. In fact, the work of Michael Manfred was supported in part by Microsoft. This is kind of the architecture of what they hope to do. And they have a well thought out plan for how this might proceed over step by step over several years with different efforts in parallel. But basically, the quantum computing part is still challenging. You have to produce the Anions and control their behavior very precisely. They have to be held at low temperature. You don't want to use that power to do housekeeping tasks of computing. So you have a classical computing layer that does the housekeeping and sort of tells the quantum part how you should move the Anions around. But then moving the Anions around does this information processing, which then you send back ultimately to interpret as classical results for drug design or optimization, traveling salesman, whatever problem you fed into it, where quantum computing can have a significant advantage over classical algorithms. This is their design. I want to show the physical arrangements, not very different from, and well, it's different in detail, but similar in spirit to the Manfred design that I showed you for the the pioneering observation of braiding. You can see that you have these gates which you can apply voltages to, and you have ways of bringing particles into and out of it. And by doing things in different orders, you're doing that. That's how you do the computations. This is similar and broadly similar in spirit to how classical computers work. The difference is you're using Anions instead of electrons. And that brings quantum mechanics into it in a big way and kind of makes the memory and the possibilities for parallel processing much bigger. So with that, I have told you what I wanted to say about Anions. I've tried to keep the discussion short and non-technical, and I'll be very happy to elaborate on things by way of questions, but I wanted to just state a conclusion, which is that grades are beautiful. So thank you very much, and I'm happy to entertain questions now.
Okay, I think I'm back. So thank you very much, Frank. Super interesting talk on a fascinating subject, of course. We do have accumulated a number of questions, so I'll read them one at a time and let you have a go at them, Frank.
Okay.
Somebody asks, I believe this is about early in the talk you mentioned the fact that in 3 dimensions, only fermions and bosons are allowed, whereas in lower dimensions, the possibilities are much greater. So the question is, why does the correction to the proof succeed for 3+ dimensions, but why does it fail for 2 dimensions? And additionally, is the one-dimensional case simply uninteresting to study, or is there any structure or something interesting going on in 1 dimension?
Okay, that's a very good question. I'm going to have to give a fairly long answer because it's profound, and so it really does make a difference. Usually, well, often, I shouldn't say usually, but often in physics, the generalization from 1 and 2 dimensions to n dimensions is fairly trivial. Like in Newtonian mechanics, it's fairly trivial to you can just make the spaces bigger, and it's not a problem. You do 4 dimensions too if you wanted to. But here, because topology is playing a role, the dimension makes a very, very big difference. So the essential thing in quantum mechanics is you have to assign what are called amplitudes to different ways that things might have happened. And then you have to sum over all the possible different ways. This is sometimes captured in the Feynman path integral. You sum over all paths with appropriate weights. So you have to multiply each path by a number, and then that's a contribution to the amplitude. Then you have to add in all the paths. So that's the fundamental way that the quantum mechanics works. This is sort of quantum mechanics at its most profound axiomatic level, kinematics. And another rule is that if you do something and then do something else along to make an amplitude, the total amplitude is the product of the amplitude for the first process times the amplitude for the second. For the individual paths, the weighting of paths has to obey that rule. Now, if you think about identical particles now, there are 2 different ways you can get from a configuration with a particle at A and a particle at B at one time to a configuration with a particle at A and a particle at B at a later time. It might be that particle A went to particle A, went to A, and B went to B, or it might be that A goes to B and B goes to A. Those are 2 possibilities. But if you have identical particles, they both started in the same same configuration and ended in the same configuration. It's just in the middle that got scrambled. And the essence of boson behavior, when you get down to this most basic level, is simply that you add those 2 possibilities with a plus sign when you have bosons, whereas if you have fermions, you add them with a minus sign. That's it. All the consequences of Fermi statistics can be traced mathematically to that basic distinction. Okay, now, in 3 dimensions, that's the only distinction you can make between different paths of particles getting from A to B. Either they've exchanged identities or they haven't exchanged identities. Another possibility is that they wind around each other several times, but in 3 dimensions, 3 space dimensions, you can always unwind. This is the fact that I mentioned that in 4 dimensions, there are no knots. So if you have 3 space plus 1 time, that's 4 dimensions, there are no knots. You can always untie them. And that may be difficult to visualize, but actually it's very simple to visualize. If you think about a knot in 3-dimensional space, it can get very entangled, but if you have an extra dimension to work with, you can think of it as that your knot, your strands can also have a temperature, say. So if you want to move one strand past another, you change the temperature, then it's not in the extra dimension, it's not in the same place, and you just move it past. So you can escape into the extra dimension and untie the knot. So in 3+1, the topology of world lines is very, very simple. But in 2+1, which is 3, we have knots. You can't untie them. And you have a structure where that's called the braid group that tells you how you combine knots. And mathematically, the relevant thing is instead of plus and minus signs, you have something called representations of the braid group, which is a much, much more forgiving structure. There are many, many more possibilities. Now, in 1 dimension, it's kind of degenerate because if you want to go move your particles past each other to exchange them or to wind them around each other, they have to pass through. And when they pass through, they can interact in all kinds of ways. So it's very difficult to distinguish topological interactions from just ordinary interactions. And physicists will know that it's very, very common in 1+1 dimensional physics to represent the same thing as either a boson or a fermion with a peculiar kind of interaction. Or you can also represent it as an anion with a peculiar kind of interaction. The whole distinction really kind of evaporates in 1 dimension. So in 1 dimension, the whole concept of quantum statistics kind of collapses. In 3 dimensions, it collapses again for another reason. But in 2 dimensions, that's the sweet spot where you can get structured complexity. So I hope that answers the question. That's as simple as I can make it. Right.
Sorry, I had muted myself. I think that's a very good answer. I guess the braids wouldn't quite be so beautiful in 1 higher dimension then. But,
well, they would tend to fall apart.
Right.
So, if the person with the braids moved their head too much, they would not have braids anymore. That's what that was. Right.
Okay. Next question. Anions are defined in 2 dimensions, but in practice, we of course live in 3 dimensions. The question is, how does the possibility of tiny movement in the 3rd dimension affect things? Can that?
Yeah, well, this is another important feature of quantum mechanics, is that you can have the 3rd dimension sort of being rigorously suppressed. That is, it takes a finite amount of energy to move at all in the 3rd direction. This is called an energy gap. Physicists will know that if you have discrete levels in a potential, there's a finite energy to get out of the ground state for motion in the 3rd dimension. And as long as your system is cold, as long as nobody gets that much energy, it's essentially rigorously 2-dimensional. Mm-hmm. Now, there are tiny corrections to this kind of behavior, but the easiest way to analyze the system is to pretend that it's 2-dimensional and take those tiny deviations as kind of a correction. They don't change the qualitative behavior.
Oh, okay. Another question pertaining to the you mentioned white dwarfs at the beginning of your talk. The question's prefaced with, this question might not make sense, but. So the question is, if in a star, electrons were anions rather than fermions, what would be the end state of a star rather than a white dwarf?
Yeah, could you, if you lived in 2 dimensions and you had any, and so you got to, well, it's not a crazy question at all, actually, because I think people will in the future, and can already to a certain extent, make physical situations in which you have many anyons in a small space, and you can try to compress them and to see if they resist. And the answer is that they do resist, not as firmly as fermions, but they tend to resist. It's only bosons that really don't resist, and in fact kind of encourage you to collapse. All other kinds of anyons put up some kind of resistance, although less than fermions. So they would still, in principle, you'd be able to support wimpy white dwarfs, maybe not so big.
Okay, perfect. Next question. How are anyons created in the experimental apparatus? I hope this person knows he's asking a question of a theorist. How are they created in an experimental apparatus which found the anionic braiding statistics?
Yeah, well, they were, so in this state of matter, the fractional quantum Hall effect, there's a preferred magnetic field to, or electron density to magnetic field ratio. This is called the filling factor. And the state of matter is perfectly realized when the filling fraction, well, I'm not going to define exactly what it means, but it's 1/3, when it's 1/3 in this particular state. Now, if the magnetic field is slightly different from that, you don't get the perfectly homogeneous uniform ground state. That's kind of the perfect fractional quantum Hall state, but you get little extra concentrations where the density changes, and those are the quasi-particles, and those are the anyons. So that the way they produce the anyons is simply by changing the magnetic field. So the density of, and also making sure no electrons escape. So you confine the electrons and apply a magnetic field, and you do that in a controlled way, and you can produce more or fewer anyons by tuning how much the filling fraction is off from 1/3.
Okay, great. Next question. How do we differentiate between different kinds of anyons in the 2020 experiments? Were multiple kinds of anyons produced, or was it only one type?
Okay, so let me answer the second one first, which is that so far only one type. The engineered enions are rather different, but they're not particles in the same sense. They're behaviors, if you like. And I think there is now, so how do they differ? There's a whole zoo of fractional quantum Hall states with different filling factors, and the magnitude of the phase that's imprinted on the wave function as one particle winds around, as one anion winds around another, depends on which state you're in. So in different states, the amount of phase you accumulate, the complex number that you get multiplied by as you move one anion around another changes. So in the 1/3 state, it's 2 pi over 3. In other states, it can be 2 pi over 5. In other states, it can even be non-abelian, which brings in another level of richness and complexity. And the way that shows up physically, well, I showed you in the experiments, you saw jumps in the current as one more anion or less, or fewer, one fewer anion is in the middle to sort of change the relationship between the contributions of the currents going up from the top and coming in from the bottom, and how they add together. In other states of matter, the jumps would be smaller. or at different places, or bigger, that sort of thing. And in the non-abelian case, it's you take the anyons after they've wound around each other, bring them together, and their probability for doing different things, annihilating or doing different things, or carrying currents in different directions, depends on which state of matter you're in, and in any particular state on how the braiding occurred. So there's a very, very rich theory of this, and the experiments are difficult, but there are many, many different things you can measure to extract information from these wave functions. But basically, they're currents or probabilities of anyons annihilating, other kinds of things that in practice are contemplated being measured.
Okay, we have quite a few questions. I hope, Frank, you're hanging in there okay, and I think we have a fair bit of time left. You're good?
This is what I was hoping for.
Great, good, okay. Next question, what would a single anion look like if we can try to visualize it? A sphere as we visualize an electron or a hadron? What is it? What is it?
Well, when I visualize an electron, I visualize just a point because in quantum field, their interactions are strictly local. So in a sense, they're structureless points, but they acquire quantum mechanical uncertainty. And so in some respects, you can think of them as being clouds also. There's a wave-particle duality, a wave-particle alternative description. Anyway, let me start from there. When protons are different, protons in our modern understanding are not points. They're made out of smaller things. They're made out of quarks and antiquarks and gluons that are doing very complicated things in a modern understanding of a proton. And they do kind of fill a finite region of space. So protons do have internal structure, and and you can study that internal structure, and it's a very rich subject with many, many people study it, and computer power is applied to it. And you can take, experimentally, you can take snapshots of the internal structure of a proton. So it makes sense to talk about it as an extended object with internal structure. Now, these anyons, which occur as quasi-particles within states of matter, ultimately are still made out of electrons and protons and ordinary matter. It's not a magic new thing that appears, but they're arranged in new and complicated ways that support this kind of behavior. Maybe I should leave it at that because it gets complicated. But in detail, they're kinds of vortices. But they're magnetic vortices. So you have charged particles being whipped around not by wind but by magnetic fields. That's their internal structure.
Okay. Next question.
They're kind of a dynamic equilibrium. I mean, electrons come in and come out, but it's this dynamic equilibrium. That's the Enion. Just as in a proton, quarks and gluons move around, and it's very, very complicated, but in the proton, there's a kind of dynamic equilibrium, a superposition of all those things rigorously. And so from the outside, it looks like just a coherent object, a proton, that you find in nuclear physics and chemistry textbooks.
Next question has to do with the transition from 2 dimensions to 3 dimensions, or 3 to 2. I'm going to slightly tweak the question a little bit. If we imagine a 3-dimensional system and we squeeze one of the dimensions, we'll eventually get a 2-dimensional system. And at what point do you go from 3-dimensional behavior to the new possibilities of 2-dimensional behavior?
Well, that's a very interesting question, and it's an area of research, actually. You can have systems with a small number of layers, 2-dimensional layers that interact with each other, and they retain some of the features of the two-dimensional system, but eventually, if motion in the third dimensions gets easier, and when you have many layers, it tends to get easier because the wave functions can spread and they're less confined. When it gets easier, this characteristic two-dimensional behavior kind of gets more obscure, less definitive, because other things, additional things can happen besides the purely two-dimensional motion, and eventually a three-dimensional starting point is better. But the transition is a very, very interesting subject. That people are exploring. There's no simple universal answer. It's different in different cases, and might offer, possibly. In fact, it certainly does offer possibilities for new discoveries, and maybe even for useful discoveries in information processing.
Such a new subject with so many possibilities. There are surely a lot of interesting things beyond what we can see now. Next question. Why do anyons pick up fractional statistics as opposed to irrational statistics?
Oh, in principle, it could be irrational. There's nothing in the principles of quantum mechanics that forbids it. But all the states of matter, to my knowledge, all the states of matter in which it's really been proposed, or all states of matter that have been shown theoretically to support anions, support just fractions. And the basic reason for that is that anions can be thought of as you inject an electron into a system, but if you just inject an electron, that's not a stable arrangement within these states of matter. The electron kind of breaks up into several pieces, in effect, in these dynamic equilibria. And it has to break up into some finite number of pieces. Or sometimes you have to inject 2 electrons and they break up into pieces. But it's always you inject an integer number and they break up into an integer number of pieces. And so you get fractions. But in engineered systems, I don't think that's necessary. I think you could get irrational fractions. You certainly can theoretically. Yeah, it's an interesting thing. I don't know that anyone has tried to engineer irrational fractions, but I'm morally certain it could be done.
Mm-hmm. Okay, the next question is, in what sense is anionic behavior in between, in quotation marks, that of bosons and fermions?
Well, it's in the sense that when you have 2 particles exchanging, say, that are identical, we get a factor of 1 for bosons, a factor of -1 for fermions, and in general, it has to be a complex number of magnitude 1. So it's what physicists call a phase. But for anions, you get a phase that's not 0, not -1, but something like, say, 1 plus I divided by square root of 2, where I is the square root of -1, the imaginary unit. So
Okay.
you get funny numbers that interpolate continuously, theoretically, between the 0 and the -1. And so in the early days, I said anything goes. And that was the origin of the anion word.
And a related question, if 1 and -1 are fermions and bosons, is there anything special about the exact halfway point where the phase would be I?
There are some special things that happen at I, but they're not so special that they may. I mean, it's distinct. It's, each. How should I say? Each kind of anion is special in its own way, and I has some special properties. I guess the most remarkable property of I of those guys is that if you put two of them together, they make a boson. And so if you know about superconductivity theory, when you have Cooper pairs, you could imagine having anion pairs that make a boson for that fraction, which is not a possibility for other fractions.
That sounds potentially very interesting.
Yeah.
Okay. Next question about the wire and the Majorana quasi-particle. Is that somehow related to the Majorana edge states of the Kitaev chain? That's not a general audience question, I think.
Yeah. Yeah, it's very much related. Kitaev first pointed to this kind of possibility of producing essentially anions, a special kind of anions called the Majorana anion at the ends of superconducting wires. Since then, other realizations have been discovered, but they all have a family resemblance to Kitaev's original proposal.
Okay.
So yeah, so that is the centerpiece really of Microsoft's long-term plan, is to use those guys. Right.
Okay. Next question, slightly long, I'll just read it. I love the topology arguments, but on a more fundamental level, why does topology get involved in quantum statistics? Is it related to the fact that particles are really excitations in quantum fields that exist in all of space-time, and that these quantum fields have topological properties, can get knotted with other fields, etc.?
Yeah, there are alternative descriptions. The particle description is the simplest to visualize. So you're thinking of particle, this is in the context, and the reason that the topology comes in is that it's in the nature of quantum mechanics. It's the fact that you can have the goal of quantum mechanics is to predict amplitudes for some things happening. And how do you do that? Well, often you take classical mechanics as a guide, and you have the classical equations of motion, and that tells you what the Lagrangian is, and then the factor you put in is e to the I times the Lagrangian technically. So classical mechanics gives you a lot of guidance, but classical mechanics comes from varying the paths just a little bit. Technically, you're looking for stationary points of the action as you vary the path. That can't tell you about how to give weights to topologically distinct classes. So you need other considerations to fix that. And that's why you can get bosons or fermions or other kinds of things. It's in the nature, and it's the topology of world lines that's the added ingredient that leads to quantum statistics. And it's there whether you like it or not. And it's just there. It was always there. People could have discovered it in 1924 once they started, or certainly by 1930 when they understood quantum mechanics pretty well. But nobody's thinking about two dimensions, and people didn't really think in this way about particle paths, finite path intuitions, so on. The field theory version is that there are certain kinds of interactions, so-called Chern-Simons terms, technically in many of these states of matter, that are possible only in 2+1 dimension, and that encode in field language the same kind of topological configurations, considerations that in the particle language are captured by the braid group.
Okay. Next question. Here's an interesting one. Not that the others weren't interesting, but could there be two-dimensional structures in the brain that give rise to anionic behavior?
Could be. I don't know of any sign of it. And of course, the brain is warm and wet. It's not a very suitable environment for quantum mechanics. And also, although in a sense the brain is two-dimensional, it's in layers that are folded. has very structured, very much two-dimensional structure, thin layer of gray matter that's been folded up. But it's not two-dimensional in this really rigorous sense of the quantum mechanical motion being totally impossible in the third, or next to impossible in the third dimension. So, it could be that some version of engineered enions are appeared in the brain, but that's a wild speculation. I don't know of any reason to think so.
Great. The next
There are easier
question.
ways to do.
The next question is asking you, what is the next frontier in Enion research that you are the most excited about?
Well, I'm interested in seeing more kinds of enions, so extensions of the Manfra experiments to other filling fractions, and especially the non-abelian ones would be very interesting. I think the really big thing that would change the landscape of the entirely and would be to find room temperature enions or enions that don't require big magnetic fields and very pure materials and so forth, or very fine engineering to produce them. And there are potentially states of matter that could support that. You can certainly write models that support it, but as yet, there's no concrete realization of that vision. But that would really change things. Then it would be easy to do topological quantum computing.
Mm-hmm. Next question, what inspired the name Enion?
Well, as I mentioned, it was this idea that you could get any phase, any complex number of magnitude 1, as you wind up one particle around another. So it was anything goes. Mm-hmm. I could mention also that there's a connection between spin and statistics. So, and this is another aspect of the whole problem, which is more theoretical, but very, very profound, which is that particles have spin, intrinsic angular momentum in quantum mechanics, usually. And there's a rule that says if the spin always has to be some whole number times h bar over 2, where h bar is Planck's constant. If that whole number is odd, then the particle is a fermion. If the whole number is even, including 0, then it's a boson. That's the rule. And it's a bizarre sounding rule, but actually you can prove it from principles of quantum field theory and moving world lines around. And in 3 dimensions, as I said, the only possibilities for spins are for the total amount of spin, the total amount of angular momentum of a particle is some whole number times h bar over 2. And this has to do technically with the fact that rotations, which govern spin and the properties of quantum mechanical spin, form are a non-abelian group. They have non-trivial commutation relations, which quantizes the allowed spins in this particular unit. In 2 dimensions, rotations are much simpler. There's not 3 dimensions of rotations. You only have one axis that you can rotate them around. That's an abelian group. And then any spin is allowed. The spin is not quantized in the same way. You can have any basic unit of spin. And it turns out that this connection between spin and statistics is very general and also true in 2 space dimension. And the fact that you can have any statistics in the sense of any phase is connected to the fact that you can have any spin in 2 dimensions.
Okay, perfect. And I'm being told that we're out of time. So I really thank everyone for their interesting questions. And there were many other questions that unfortunately couldn't be answered. So I think I now turn the hand the microphone to my colleague, Rob Thompson, to thank you. But I'll just give a personal thank you so much, Frank, for accommodating us here. This was really terrific.
It was a pleasure to talk about this subject, and thank you for your introduction. Thank you for the invitation, and thanks to the audience for some very probing and intelligent questions.
Okay, so Rob, I'll turn it over to you, and talk to you soon, Frank.
Thank you very much, Richard. And thank you so much, Frank, for such an interesting talk and a really engaged discussion session there for the last half hour or so. Frank, if we could prevail on you to do a little bit of homework, we have copies of the questions we weren't able to pass on to you. Maybe we could send those to you and you could write us a couple quick responses that we could post on the conference website.
Happy to respond, but it probably won't be quick. I have some urgent business the next few days, but yes.
Yes. Regardless, thank you so much for the talk. As is our tradition, we will, since we can't hand it to you, we will be sending you a copy of Herzberg's official biography, autographed by the author, for you to learn a little bit more about him that you might not know, and just as a keepsake and thank you for taking on this talk for us. So thank you very much. Along the lines of thank yous, I would like to explicitly note and thank the Simon Fraser University team who have acted as virtual hosts and have run all the technical aspects of this very successful virtual version of the Herzberg lecture. I would also like to acknowledge our sponsors of both the lecture and of our Congress, which include Triumph, University of Waterloo, Snow Lab, Perimeter Institute, Institute for Quantum Computing, Gamble Technologies, Canadian Journal of Physics, and Macmillan Learning. And beyond that, I need to issue one last thanks, which is to everybody who was here this afternoon / this evening, depending where you were in the country. Thank you for coming out and joining us for our annual Herzberg lecture, and we hope that you have a very enjoyable rest of your evening. Thank you so much for coming out. Goodbye now.